Before we go deeper to the effect of Chatelier's principle to an equilibrium system, let's see what Chatelier's principle is. By definition, Chatelier's principle states that if a system at equilibrium is subjected to a change, for example, change in concentration, pressure, or temperature, the system will react to counteract or to overcome the change. As we already looked at in the objective 6.3, the Chatelier's principle, there are factors that affecting an equilibrium position. The first one is the concentration. The second one is temperature. The third one is pressure and volume. And the fourth one is a catalyst. So there are four factors that we will look at after this that will affect the equilibrium position when there is changes to the system. The first factor changing the concentration of the components in an equilibrium system. So, increasing the concentration of a reactant will shift the equilibrium position toward the product formation or to the right. Let's look at the example. Increasing the concentration of reactant A will shift the reaction to the right, to the product formation. And increasing the concentration of a product will shift the equilibrium position towards the reactant formation, which is to the left. Let's look at the example. Increasing the concentration of product will shift the equilibrium position towards the reactant formation to the left. Next, what about decreasing the concentration of the reactants? Firstly, decreasing the concentration of the reactant will shift the equilibrium position toward the reactants formation. Focus on the example below. Decreasing the concentration of A will shift the equilibrium position from right to the left to the formation of reactant A. Decreasing the concentration of a product B here, will shift an equilibrium position towards the product formation, which is to the right. So look at the example carefully. Decreasing the concentration of B will shift the equilibrium position towards the formation of B, towards the formation of product. Let's look at the example, the synthesis of hydrogen iodide. If we increase the concentration of hydrogen gas, the equilibrium system will be disturbed, which is more hydrogen gas will react with iodine gas to form more hydrogen iodide. So as a result, the equilibrium position shifts to the formation of hydrogen iodide or shift to the right. Okay students, let's do some activities. Look at the example below. We have reactant A and B will react together in a reversible reaction to form product C and D. And after some time, the reaction achieves equilibrium. But while the system is in equilibrium, we disturb the system by making some changes, and you should predict where is the shifting of the equilibrium position. Let's do it together. Firstly, what will happen when we increase the concentration of the products? either C or D. Yes, the equilibrium position will shift to the left. Next, what will happen when we decrease the concentration of the product, either C or D? Yes, the equilibrium position will shift to the right. Next changes, what will happen when we increase the concentration of the reactants, A and B? Yes, the equilibrium position will shift to the right also. And lastly, what will happen when we decrease the concentration of the reactants? Excellent, the equilibrium position will shift to the left. Congratulations to the students who already answered all the questions correctly. In previous slide, we already looked at how the changes in concentration of the reactants will affect the equilibrium position of the system. Now let's look at the factor number 2, the temperature, the changes of temperature. Firstly, let's look at the definition. Changing the temperature of a system at equilibrium will change the energy content of both reactants and products relative to each other. So what does it mean? We look at the next slide for the example. Students, you are familiar with endothermic reaction and exothermic reaction. Do you remember what is endothermic reaction and exothermic reaction? Let's look at the slide. Endothermic reaction, the definition, is when the chemical reaction that absorb heat from the surrounding. It is a chemical reaction that absorb heat from the surrounding. We call it as endothermic reaction. What about exothermic reaction? Exothermic reaction is a reaction in which the system, give off heat to the surrounding. So any reaction that release heat, we call it as exothermic reaction. So what changes in temperature will do to the equilibrium position? Before we go deeper, please remember that only temperature change can alter the constant K, the equilibrium constant. If you change the concentration of reactants or product in an equilibrium system, it will not change the equilibrium constant K. Only changing the temperature will change the equilibrium constant K. So we look at a reversible reaction here. The first reaction showing that PCl3 reacting with Cl2 will forming PCl5, it is a reversible reaction. And it's showing that delta H has negative or minus symbol. It means the forward reaction for this reversible reaction is an exothermic reaction. So if we break the equation into two equations, which is first one is the forward reaction and the second one is the reverse reaction. So let's look at the first one first. PCl3 reacting with Cl2 forming PCl5, it is a forward reaction. It is an exothermic reaction which is heat release in forming PCl5. As we go to the second equation, which is a reverse to the reaction, which is PCl5 now forming PCl3 and Cl2. The reverse to the reaction is an endothermic reaction indicated by delta H here, or the reverse reaction will need heat to do the reaction. As we look at in the graph, the exothermic reaction, you can see that during the reaction, heat is released to the surrounding. So this is exothermic reaction. While in endothermic reaction, starting with the reactants, heat is increasing, heat is absorbed into the system. So it is an endothermic reaction. Now let's go to our real business. What changes in temperature do to the equilibrium position? Now let's focus on exothermic reaction. Given to you the equation, we know the exothermic reaction when heat is released. For example, in this reaction, it is an exothermic reaction indicated by the symbol here. The forward direction is an exothermic reaction. Okay. Disturbance to the system. What will happen when we rise temperature? When we increase the temperature of the system, it means we are adding heat to the system. So, the exothermic reaction is not favorable. Exothermic reaction will release heat. If we add more heat, it is not favorable to exothermic reaction. Thus, the reaction will shift from right to the left. The equilibrium position will shift from right to the left. However, in exothermic reaction, look at the example equation. When we decrease the temperature or drop in temperature, we remove heat from the system. So, exothermic reaction is favorable, which is the forward direction is favorable. So, reaction will shift from left to the right. The equilibrium position will shift from left to the right. In previous slide, we already looked at the exothermic reaction system. What changes in temperature, increase or decrease in temperature will do to the equilibrium position in an exothermic reaction. Now let's move on to what will happen when we increase or decrease temperature in an endothermic reaction. As we looked at before, endothermic reaction is a reaction when it absorbs heat. And we can say the reaction is endothermic when we look at delta H and it has a positive symbol. So, any disturbance to the endothermic reaction, for example, if we rise the temperature, if we increase the temperature to an endothermic reaction, it means we are adding more heat to the system. So, endothermic reaction is favorable as the reaction needs heat to proceed. Thus, the equilibrium position of the reaction will shift from left to the right, to the forward direction. Next, we still in endothermic reaction. What will happen when we decrease the temperature in an endothermic reaction? Decreasing temperature, it means we are removing heat from the system, so the endothermic reaction is not favorable. It will not move forward. Therefore, the reaction will shift from right to the left. The equilibrium position will shift from right to the left. Now, let's look at in a real reaction. Look at the example with the yellow box and the brown box. The forward reaction for the reaction is an endothermic reaction, and the reverse reaction thus is an exothermic reaction. Increasing temperature will produce more product because it is an endothermic reaction, while increase in temperature will shift the equilibrium position to the right. So you will see the reactant will fade away and you will see more brown colors. Meanwhile, decrease in temperature will reverse the reaction, as decrease in temperature is not favorable in endothermic reaction. Decrease the temperature will reverse the reaction. So now the equilibrium position will shift to the left. So you will see the brown color lightens as the temperature of the system decrease. Okay students, next part we will look at how changes in temperature will change the value of equilibrium constant capital K. Let's look at the example given. We are given with chemical equation PCl3 reacting with Cl2 forming PCl5, and it shows an exothermic reaction. Firstly, let's write down the equilibrium constant Kc. Equilibrium constant K is equals to concentration of product over concentration of reactants. Changing the temperature of the system. Firstly, let's look at what will happen when we change the temperature of the system. When we increase the temperature, the net reaction, the equilibrium position will shift to the left. And what does it mean? It means that our concentration will decrease in our product. The concentration of the product will decrease in value, and our concentration of reactants will increase in value. So we can see a smaller value for a smaller number on the top and a bigger number on the bottom of the fraction will give a lower K. So K will decrease when we increase the temperature of the system in exothermic reaction. What about if we decrease the temperature of the system, of the exothermic system? The equilibrium position will shift to the right. What does it mean? It means that our concentration of product will increase in value. Meanwhile, our concentration of reactants will decrease in value. So in a fraction calculation, when we have a bigger number on the top of the fraction, when we have a smaller number on the bottom, it will give a bigger value. So equilibrium constant Kc will increase when we decrease temperature. It means that temperature decrease favor an isothermic reaction as the equilibrium value increasing. Just now we already looked at the isothermic reaction. Now let's move on to endothermic reaction. We are given with the example to endothermic reaction. We have SO2 in a reversible reaction forming S sulfur and O2 gas, and it is an endothermic reaction. Let's write down the equilibrium constant for the reaction Kc. So Kc is equals to concentration of product. We have O2 here and divided by concentration of SO2. Note that the sulfur is not involving in equilibrium constant calculation because sulfur has a constant concentration. So it is not involved in the calculation. So let's see what will happen. What will happen when we do changes in temperature to an endothermic reaction? In an endothermic reaction, if we increase the temperature, we already know that the equilibrium reaction will shift to the right. Increase in temperature in endothermic reaction will shift the equilibrium position to the right. What does it mean? It means the concentration of product will increase and the concentration of the reactant will decrease. So in a fraction calculation, when we have a bigger number divided by a smaller number, it will give a bigger number. So K, equilibrium constant K, will increase when we increase the temperature in an endothermic reaction. Next, let's look at when we decrease the temperature in an endothermic reaction. We know that decreasing temperature will shift the equilibrium position in endothermic reaction to the left. What does it mean? It means that our concentration of product will decrease and our concentration of reactant will increase. When we divide a smaller number to a bigger number, it will give a smaller number. So the equilibrium constant K will decrease when we decrease temperature in an endothermic reaction. Therefore, we can conclude that temperature increase will favor endothermic reaction as the equilibrium constant will get bigger, so it means our product are increasing. Just now we look at endothermic reaction and exothermic reaction, the effect of temperature to endothermic and exothermic reaction. However, there is some reaction, some chemical reaction that is non-exothermic or non-endothermic. For example, given to you here, this is the hydrolysis of ester. It is non-exothermic and non-endothermic. So the change in temperature will not change the equilibrium position in the reaction. Here are some exercises for students to try. You can check your answer with your teacher. Last part, changes in temperature, referring to the Chatelier's principle. It's just a summary. When we increase the temperature in an isothermic reaction, it will decrease the equilibrium constant K. Meanwhile, when we increase the temperature in endothermic reaction, it will increase the equilibrium constant K. Decrease in temperature in isothermic reaction will increase the equilibrium constant K, while decreasing the temperature in endothermic reaction will decrease the equilibrium constant. How it is calculated, you can refer to the previous slide. For a system with gaseous components, changing the pressure is possible by two ways, which is changing the volume of the reaction vessel and also by adding an inert gas in the reacting vessel. By referring to the Chatelier's principle, equilibrium position will overcome the increase in pressure. So from the equation above, increase in pressure will shift the equilibrium position to less number of gas molecule. Look at the example in the equation. Increase the pressure will shift the equilibrium position to less number of gas molecule. Let's look at how pressure and volume are related. Look at the example. We have a container in the middle. Lower the pressure, it means we are increasing the volume. Lower the pressure or higher volume will cause more number of mole of gases. Meanwhile, higher pressure or lower volume will cause fewer number of gases. It is related by the pressure is inversely proportional to volume. You already look at this equation in gas law in chapter 5. From the example before, we can relate with the example given, N2O4 becoming 2NO2. When we increase the pressure or we decrease the volume, more collision will take place between gaseous molecules. As the pressure is a measure of number of particles per unit volume, so the rate of reaction increase. However, the equilibrium constant will remain unchanged. We already looked at before, the equilibrium constant will change only on the changes of temperature. Let's look at the given reaction, N2O4 becoming NO2. In the above reaction, when pressure is increased, the equilibrium position will shift to the less number of mole, which is to the left. When pressure is increased, the reaction will shift to the less number of mole, so in this case, to the left. If we decrease the pressure or by increasing the volume, the equilibrium position will shift to more number of mole, which is to the right. So if we decrease the pressure, the equilibrium position will shift to more number of mole of the gases, which is in this case to the right. Please remember that the pressure changes only will affect the system with different number of gaseous molecule on the reactants and the product side. Pressure changes are irrelevant if there are no gas molecule in the reaction. Let's look at the example. For example, we have H2 gas. It is H2 gas and I2 gas in the reactant side. Total number of mole of gas is 2, becoming 2 mole of hydrogen iodide. We can see there is no change in the number of mole of gases at the reactants and the product. Or we can say the number of mole of gases in the reactants and the number of mole of gases in the product are same. So changing the pressure will not change the equilibrium position of the reaction. Here the summary to changing of pressure in a gaseous system. If we increase the pressure, the equilibrium position will shift to the side with fewer number of mole of gas. If we decrease the pressure, the equilibrium position will shift to the side with more number of mole of gas. If we increase the volume or we decrease the pressure, the equilibrium position will shift to more number of mole of gas. And if we decrease the volume or we increase the pressure, the equilibrium position will shift to fewer number of mole of gas. The effect of a noble gas on equilibrium at constant volume. At constant volume, when inert gas are added, the total number of gaseous molecules increases. So the total pressure of the equilibrium system also will increases. However, the partial pressure of each of the gases in the equilibrium system will remain unchanged. This will lead to addition of inert gas at constant volume has no effect on the equilibrium position and the composition of the equilibrium mixture. It's time for exercise. You can do the exercise and you can check your answer with your lecturer. the last part of our lecture, the effect of catalyst to the equilibrium position in equilibrium system based on Le Chatelier principle. Before we go what catalysts do to an equilibrium system, let's see what is catalyst. Catalyst is a substance that increases the rate of a chemical reaction but are not used up in the reaction. How it increases the rate of chemical reaction? Catalyst will provide an alternative pathway. For example, this reaction, this is the pathway for the reaction to go forward. We can see it has a high barrier for the reaction to go. When we add the catalyst to the system, the catalyst will provide alternative pathway with a lower barrier. The barrier, we call it as activation energy. So, in the presence of catalyst, it will provide an alternative pathway for the reaction to go from the reactant to product. So, as the barrier is lower, the reaction will go easier than without the catalyst, without the uncatalyzed system. So, to summarize what we already looked at in previous slide, catalyst speeds up a reaction. It provides alternative mechanism or alternative pathway in a reaction with a lower activation energy. So it increases the forward and reverse rate of reaction to some extent. It shortens the time for the reaction to reach equilibrium, but however, catalyst has no effect on the equilibrium position and the value of equilibrium constant K. To recap the summary in previous lecture, let's do this exercise. So, what will you expect to the pressure of the system when the catalyst is added to the system? So, let's see. Adding a catalyst will not change the value of equilibrium constant K. So, it will not shift the position of an equilibrium system. However, the system will reach equilibrium sooner because it has a lower, it follow the pathway of the reaction with lower activation energy. Here the summary, what we already looked at in previous slides on Le Chatelier principle. Changing of concentration will shift the equilibrium position, yes. However, it will not change the value of equilibrium constant. Changing in pressure in the system will shift the equilibrium position, but it will not change the value of equilibrium constant. Changing the volume in the system will shift the equilibrium position but will not change the equilibrium constant value. Changing the temperature will shift the equilibrium position and also it will change the equilibrium constant value. And adding the catalyst to the system will not do any changes to the equilibrium position and the equilibrium constant value.
Le Chatelier's Principle. Remember our example on equilibrium attained on an escalator? You are going up on an escalator which is coming down at same speed. Thus, you appear to be a fixed point on the escalator. Suppose your mischievous friends decide to increase the speed of the escalator. In order for you to still remain at the same point, you will have to increase your speed to match the speed of escalator and attain the dynamic equilibrium again. Le Chatelier, a French chemist, first noticed this phenomenon of restoring balance in chemical reactions. He observed that a system always acts to oppose changes in chemical equilibrium. If stress is placed on a system at equilibrium, the system will proceed in the direction that maximizes the stress and helps in restoring equilibrium. Stress can be applied on a chemical reaction by changing concentration, temperature, or pressure. Concentration can be changed by adding reactants or products to a reaction. If you add reactants, the system will start creating more products to reduce concentration of reaction and restore equilibrium. If you add products, the backward reaction will start occurring at faster rate to reduce concentration of products and restore equilibrium. For example, two different colored cobalt complex ions COH2O6 and COC4 exist together in equilibrium in an aqueous solution in the presence of chloride ions. This equilibrium can be distributed by changing the chloride ion concentration or changing temperature. If you increase concentration of chloride ions by adding more HCl, more products will be formed and solution will turn blue. If you add more water, reaction moves backwards and solution turns pink. Temperature impacts an equilibrium on basis of the direction of endothermic and exothermic reactions. If temperature is increased, system will move in the direction which absorbs heat, thus favoring endothermic reaction. If temperature is decreased, system will move in the direction which releases heat, thus favoring exothermic reaction. In our above example of cobalt-2 ions, forward reaction is endothermic and backward reaction is exothermic. If you increase temperature, forward reaction occurs more rapidly to absorb the heat and solution turns blue. However, if you decrease temperature, reaction moves backwards, turning the solution pink. Finally, for gases, we can also induce stress by applying pressure. Increasing pressure on system at equilibrium forces it to move in the direction with less number of molecules. For example, in the process of creation of ammonia gas, one molecule of nitrogen gas combines with 3 molecules of hydrogen gas to form 2 molecules of ammonia. Here, number of molecules of reactants are 4, while number of product molecules are 2. Thus, if you apply pressure, system will create more ammonia, reducing the number of molecules. And if you release pressure, backward reaction will be favored. There are certain non-factors which, if introduced in a system at equilibrium, have catalysts, have no impact on equilibrium because they impact both forward as well as backward reactions equally. Similarly, inert gases also have no impact on equilibrium. That's all you need to know about chemical equilibrium.